Dear students, in this module, I will present an example for you regarding the Zuker's algorithm. As you would remember, Zuker's algorithm is used to evaluate the stability of RNA secondary structures. So in the Zuker's algorithm, what you do is you have the negative energy values that come from the coupled nucleotides, and you have the positive energy values that are coming in from unpaired nucleotides. And you sum them up to arrive at a single number for one secondary structure. You repeat this process for different secondary structure possibilities, and you list down the energy values, and of course you select the one with the most negative energy or the lowest energy. Dear students, this is an example from your textbook that I would like to solve for you. Here, as you can see, the RNA sequence has been provided for you on the left side in a table. The same sequence is also written on top, but as you can see, for the sake of brevity, I have omitted the remaining portion of the RNA. What we will do is we will try to see how many possible combinations exist for the nucleotide coupling. Let's see. So A can couple with U on the 3' end. This A is of course at the 5' end, as you can see here. So we will write it down as A/U, and this will be represented and written in the table for you. Next, we'll find out the next complementary pair. In this case, it is C and G. C is coming from here, and G is coming from here, and so on and so forth. So we will fill this entire table up with complementary combinations. If you look at the table given below for the stacking energies for base pairs, you can see that AU couple that is shown here actually gives out minus 1.8 kilocalories, and if it is followed by a C or G as shown by this red box, then we can put this value in an energy table that is shown on the right side. Here, this value has been placed against the complementary couple. So minus 1.8 kilocalories is given out if A and U is followed by C and G. You can continue building on this table of free energy calculations. In the case of C and G followed by G and C, C and G followed by G and C, the energy that is given out is minus 3.4. So the net overall energy of the molecule will be minus 1.8 that was obtained earlier, shown here, minus 3.4 that is shown here, and this will be equal to minus 5.2, which is written here. In this way, you can continue to fill this table, and you can fill the next box with minus 6.4, and so on and so forth. If you look carefully at the bottom of this table, there is a destabilizing energy as well that we will use in a moment. So the structure that is formed is A is coupled with U here, G is coupled with C here, another C is coupled with G here, a U is coupled with G shown here, and then there are some nucleotides that are uncoupled. Remember, in Zuker's algorithm, we have to incorporate the instability introduced by these unpaired nucleotides. For that, you can simply count them up. So in this case, they are 5. So it's a hairpin, right? So if there are 5 nucleotides, right, which are unpaired, then you can add 4.4 kilocalories to the overall energy profile. So the stabilizing energy in this case is minus 6.4, and the destabilization energy is plus 4.4. If you add them up, you will arrive at the overall energy of the molecule. So we just calculated the energy for one 2' structure, and you can do it for all other possibilities that exist. You must remember that you have to construct all the possible combinations and then compare the energy profiles of each molecule.